The content in this presentation is covered on pages 146 through 147 of your textbook, and it's meant to help you achieve learning objective number 22, which is to describe the adiabatic temperature changes and explain why the wet adiabatic rate of cooling is less than the dry adiabatic rate of cooling. So be sure to skim pages 146 through 147 before you watch this video. Especially focus on the definition of adiabatic. It's a change in temperature without losing energy to the atmosphere. And that's a little bit hard to wrap your head around initially, but we'll be talking about this in lab too. Remember that condensation occurs when there is enough water vapor added to the air, or more commonly, when the air is cooled to its dew point temperature. Condensation can produce dew or fog or clouds. Heat near Earth's surface is readily exchanged between the ground and the air above. As the ground loses heat in the evening through radiation cooling, dew forms on the grass, while fog may form slightly above the Earth's surface. So you can see that the surface cooling that occurs after sunset produces some condensation. Cloud formation, however, often takes place during the warmest part of the day, an indication that another mechanism must be operating aloft that cools air sufficiently to generate the clouds. The process that generates most clouds is easily visualized if you can imagine pumping up your bike tire with a hand pump. Have you ever noticed that when that occurs, the pump barrel will increase in temperature? It becomes warm. When you apply energy to compress the air, the motion of the gas molecules increases and the temperature of the air rises. Conversely, if you allow air to escape from a bicycle tire, the air expands, the gas molecules move less rapidly, and the air cools. And you might even see condensation happen. I know you probably have also experienced the same phenomenon. The cooling effect of, say, a propellant gas, hairspray, that canned air dusting stuff that you get at Radio Shack for your keyboard. When you squeeze the gas out of those canisters, your hand feels really cold. When an aircraft passes through the air, it causes a series of pressure waves in front of it and behind it, similar to the bow and stern waves that you see created by a boat. Those waves will travel at the speed of sound, and as the speed of the object increases, the waves are forced together or compressed like the air inside that bike pump, because they can't get out of the way of each other. If the aircraft travels fast enough, the waves merge into a single shock wave, which travels at the speed of sound, and when there's a smooth flight, the shock wave starts at the nose of the aircraft, where there's dramatic increase in pressure, and ends at the tail, where the pressure is much lower and even negative in value. The pressure returns to normal after the object passes, and a boom is experienced along with the sudden change in pressure. It's actually two booms, one when the pressure increase reaches the observer, and another when the pressure returns to normal. So when the localized air pressure around the object drops, so does the air temperature. and that causes a rapid condensation, right? We know that dropping the air temperature will cause condensation in a valve in a flask on our desk. And we'll see a little cloud form. That cloud's called a vapor cone, and it forms all around the aircraft, just like is surrounding this F-18. The temperature changes that we're talking about, in which heat energy hasn't been added or subtracted, are adiabatic temperature changes. Okay. So instead, we see changes in pressure result in temperature changes. And when the air is compressed, it warms. And when the air is allowed to expand again, it cools. So that's kind of a lot. I try to find some visual cues for you to remember these things. But it doesn't always work. I think what works best is reading the content of these texts. You might have to read this section a couple of times to really understand it. But talking about adiabatic cooling and condensation, imagine a volume of air enclosed in a thin balloon. In meteorology, we call this an air parcel. Typically, we consider a parcel to be a few hundred cubic meters in volume. We assume that it acts independently of the air surrounding it, but it has its own sort of temperature and moisture conditions that are different from the air in the environment around it. So we assume that there isn't any heat being transferred into or out of this parcel. Although this image is highly idealized, over short time spans, a parcel of air behaves much like an actual volume of air moving up or down in the atmosphere. In nature, the surrounding air sometimes infiltrates a rising or descending column of air, and that's a process called entrainment. But for this discussion, we assume that there's no mixing that happens through this process. So that little gray bubble that you see kind of moving up and down in this picture is closed, a closed container. Remember that from early on in this class, we talked about atmospheric pressure and how it decreases with height above the ground surface. Anytime a parcel of air moves upward, it passes through regions of successfully lower pressure. So we think of different layers. The layer near the ground has high pressure. The next layer above has lower pressure. The next layer above that even lower. So we consider that to be stratified air because it's layered. Strata means layer. As a result of passing through those different layers of pressure, the air, as it ascends in this parcel, expands. And because it expands, the volume increases. There's cooling going on. That is adiabatic cooling. So it's not trading or exchanging any temperature with the environment around it. It's adiabatic cooling. The unsaturated air cools at a constant rate of 10 degrees C per 1,000 meters of ascent. The descending air comes under increasing pressure, and it compresses and heats by 10 degrees C per 1,000 meters of descent. So that rate of cooling or heating applies only to the unsaturated air, and it's known as the dry adiabatic rate because the air is not saturated. we call it dry. And so it's abbreviated like it is in this slide as the DALR, the dry adiabatic lapse rate. Okay, so that's a big alphabet soup, a tricky word to say. It definitely impresses people when you work it into a conversation. But that's the sort of the grown-up, the college course term for air cooling in a parcel as it rises or heating as it sinks. Why is the wet adiabatic rate not constant? All right, this is a tricky issue, but once saturation begins, we lose latent heat energy. Let me go through this a little bit more carefully. So if an air parcel rises high enough in the atmosphere, and you can see this is just like the last slide, we're cooling at 10 degrees C per 1,000 meters. So here's 22 degrees C at 1,000 meters. That tells me that I know that the surface must be 32 degrees C. So it's a warm day. If I go all the way up to 2,000, I've lost another 10 degrees C, so I'm at 12 degrees C. And by the time I'm at 3,000 feet, I'm at 2 degrees C. So if that air parcel rises high enough, and in this case it has risen that high, it cools to its dew point, and we see condensation occur. So the altitude at which a parcel reaches saturation and cloud formation begins is known as the lifting condensation level. So if that parcel is lifted to this level, condensation will occur. Sometimes we don't even use the word lifting, but we just say condensation level. At that level, an important change occurs. The latent heat that was absorbed by the water vapor when it was evaporated is released. And all of a sudden, it's not latent anymore. Now you can feel the temperature. It's sensible heat. So we can measure it with a thermometer. Although the parcel continues to cool adiabatically, the release of the latent heat lowers the rate of cooling. So now we're above the condensation level, and we see a different rate. Right here is the wet adiabatic lapse rate, and it's cooling now at 5 degrees C because we've reached saturation. Okay, so if we go from +2 to -3, we know we've gone up another 1,000 feet. And as we go all the way up to 5,000, another 1,000 feet, we'll decrease another 5 degrees C. Okay, that's a sign that we're doing wet adiabatic lapse rate. So below the condensation level, no clouds. At the condensation level, we switch from the dry adiabatic lapse rate to the wet adiabatic lapse rate, and now we start to see water vapor turning into liquids, droplets, clouds. Because the amount of latent heat release depends on the quantity of moisture present in the air, and that can be anywhere between 0.01 and 4%. The wet adiabatic rate varies, right? So if there's more water in the atmosphere, it makes sense that we'd see a different lapse rate. But in general, 5 degrees C is about as low of a wet adiabatic rate as we'll ever see. If we really have dry air and we see clouds forming, under those arid conditions, low moisture content air might cool at a wet adiabatic rate of 9 or so degrees C. The figure here, though, illustrates that role of adiabatic cooling in the formation of the clouds. So rising air cools at the dry adiabatic rate from the surface all the way up to the condensation level, and then it starts to cool at the adiabatic, wet adiabatic lapse rate. And if we're someplace like the tropics, where we have really moist air, we'll expect that wet adiabatic rate to be something like 5 degrees C. And if we're not, if we're over central Mexico or Arizona, we might see a wet adiabatic rate as fast as 9 degrees C per 1,000 meters, but not quite as fast as the dry adiabatic rate. So use the content in the Canvas site and any of the outside or other sources to verify that you can answer these questions. If you can answer them and answer them without any trouble, you're in great shape for the test. If you can't, reread that textbook, rewatch the video, and see if your skills improve. If you're still completely stumped, though, make sure you either start a discussion on the Canvas site or come and ask me for help.